In this video, we are continuing with the trends in the atomic properties of the first transition series. Also, we will be studying about inner transition elements. So we are continuing with the trend. So the next trend is color. We know that any substance which appears colored is because that particular substance absorbs the portion of a visible light, and the color depends upon the wavelength of absorption in the visible region of electromagnetic radiation. Because of the formation of ionic and covalent compounds, transition elements are colored, and the main reason behind this is the unpaired electrons which are present in the d orbital. When the atoms are free or isolated, the 5 d orbitals which are present, they are at the same level with the same energy, and hence they are called as degenerated d orbitals. But when we consider complexes, we know that there is a central metal ion, and the central metal ion is surrounded by solvent molecules or ligands. And these surrounding molecules affect the energy of the d orbitals, and the energy of these orbitals is no longer the same. When they start bonding with the ligands, the different symmetries of the d orbitals split apart and they become non-degenerate, which means that now they are not at the same level, they split up. When an electron jumps from a lower energy d orbital to a higher energy d orbital, which means there is dd transition taking place, the energy of the excitation of electrons corresponds to the frequency of the light absorbed. So the small amount of energy which is required for the transition is available by absorption of radiation having certain wavelength from the visible region. The remaining light is then transmitted, and the observed color of the compound corresponds to complementary color of the light absorbed. For example, if red color is absorbed, then the light which gets transmitted contains various colors in the spectrum, particularly blue. Hence the compound is going to appear blue in color. The elements of transition series which have no unpaired electrons present in the d orbital, then they appear colorless. Let us consider some example to understand the trend of color. Always keep in mind, the color of a compound depends upon the nature of the ligands and geometry of the complex. Let us consider the example of cobalt chloride. When cobalt chloride is dissolved in water, it forms a pink solution of the complex CO bracket H2O 6 times bracket close and raised to 2 plus, that is the oxidation state of cobalt. This complex formed has an octahedral geometry. When the solution is further treated with hydrochloric acid, it turns deep blue. And the reason behind this is there is a formation of another complex, that is COCl4 bracket close raised to 2 minus. And this complex has a tetrahedral structure. So this was one example wherein you saw that when there is formation of complex taking place, and depending upon the geometry, the color changes. So in short, you can say the color of the transition metal ion relates to presence of unpaired d electrons, dd transitions, the nature of ligands attached to the metal ion, and the geometry of ions formed by the metal ion. Here is a table which gives information regarding the color of 3D transition metal ions. So you can see that the 3D series is mentioned here, starting from scandium ending with zinc. The number of unpaired electrons in the d orbital are also mentioned. You can observe here scandium, titanium 4 plus ion, copper plus ion, zinc 2 plus ions have 0 unpaired electrons, and that is the reason that they are colorless, while rest of the ions, they are colored. Now we move on to the next trend, that is catalytic properties. Transition metals and their compounds exhibit very good catalytic properties. They act as homogeneous and heterogeneous catalysts as well. Compounds like iron, cobalt, platinum, palladium, chromium, nickel, etc. are used as catalysts in a number of chemical reactions, and these compounds increase the rate of a chemical reaction. In homogeneous catalysis reaction, the metal ion participates by forming an unstable intermediate, whereas in heterogeneous catalysis reaction, the metal provides a surface for the reactant to react. Here are some examples. Manganese dioxide acts as a catalyst for the decomposition of potassium chlorate. In the production of ammonia by Haber's process, iron or molybdenum is used as a catalyst. Cobalt-thorium alloy is used in the Fischer-Tropsch process for the synthesis of gasoline. Finely divided nickel is used as a catalyst in the hydrogenation of ethene. In the contact process for the synthesis of sulfuric acid, sulfur dioxide reacts with oxygen in the presence of platinum asbestos, which act as a catalyst. Carbon dioxide and hydrogen are formed by the reaction of carbon monoxide and water at 500 degrees Celsius using iron and chromium as catalyst. So this was all about the catalytic properties. Now we move on to the next trend, that is formation of interstitial compounds. What are interstitial compounds? When small atoms like hydrogen, carbon, nitrogen are trapped within the interstitial spaces of the crystal lattice, then they are called as interstitial compounds. Sometimes even sulfides and oxides are trapped in the interstitial spaces. Steel and cast iron are examples of interstitial compounds of carbon and iron. Due to the presence of carbon, the malleability and ductility of iron decreases, whereas the tenacity increases. Tenacity is the resistance which wires experience when passed at equal temperature through the same hole. Interstitial compounds are hard and they are good conductors of heat and electricity. Their chemical properties are similar to the parent metal. The melting points of the interstitial compounds are higher when compared to the pure metal. Their densities are less when compared to the parent metal. The metallic carbides are chemically inert and are hard as diamond. Hydrides of transition metals are used as powerful reducing agents. So this was all about the formation of interstitial compounds. The last trend is formation of alloys. Transition metals form alloys where atoms of one metal are distributed randomly in the lattice of another metal. Metals with similar radii and properties form alloys. Alloys are of two types, ferrous and non-ferrous. Ferrous alloys have atoms of other elements distributed randomly in the atoms of iron. Since here the percentage of iron is more, it is termed as ferrous alloy. Example of ferrous alloys are nickel steel, chromium steel, stainless steel, and all this steel contain 2% of carbon. Next are the non-ferrous alloys. These alloys are formed by mixing atoms of transition metal other than iron with a non-transition element, which means any other element apart from D block. Example of non-ferrous alloy is brass, which is a mixture of copper and zinc. Let us now study the uses of ferrous and non-ferrous alloys. Bronze is an alloy which is made up of copper and tin. It is tough, strong, and corrosion resistant. It is used for making statues, medals, and trophies. Cupra nickel is an alloy which is made up of copper and nickel. This alloy is used for making machinery parts of marine ships, boats, etc. For example, the marine condenser tubes. Stainless steel is an alloy which is used in the construction of fuselage of ultra-high-speed aircraft. Nichrome is an alloy made up of nickel and chromium, and it is used in gas turbine engines. Titanium alloys can withstand high temperature, and hence it is used in ultra-high-speed flights, fireproof bulkheads, and exhaust shrouds. Let us now study some properties of D block elements. First we shall study the physical properties and then we study the chemical properties. So the physical properties of D block elements are as follows. All the D block elements are lustrous and shining. They are hard and have high density. They are good electrical and thermal conductors. Thermal conductors means heat. They have high tensile strength and malleability. D block elements can form alloys with transition as well as non-transition elements. Many metals and their compounds are paramagnetic, which means that they get attracted towards the magnetic field. Most of the elements of D block act as catalyst. Let us now move on to the chemical properties of D block elements. So all the D block elements, they are electropositive. They exhibit variable valencies and form colored salts and complexes. D block elements act as good reducing agents. They form insoluble oxides and hydroxides. Iron, cobalt, molybdenum, zinc are all biologically important metals. D block elements also catalyze biological reactions. There are some differences which are observed in these transition metals. The elements present in the first row differ from the second and third row in terms of stabilization of oxidation states in their compounds. Let us now study a very small topic, that is extraction of metals. We know that most of the metals are present in the Earth's crust. They are in the form of salts like carbonates, sulfates, sulfides and oxides. There are few metals which are non-reactive and they occur in the free state in the Earth's crust. For example, gold, silver and platinum. What is a mineral? It is a naturally occurring substance which is found in the Earth's crust containing inorganic salts, solids, siliceous matter, etc. Siliceous means silica is present in them. What is an ore? The mineral which contains high percentage of metal and from which the metal can be extracted economically is called as an ore. Here is a table which gives the minerals and ores of some transition metals. So the first metal is iron and the minerals are hematite, magnetite, limonite, iron pyrites, siderite. Their molecular formulas are given besides them and the ore which is extracted from it is hematite. Next is copper. So the minerals are chalcopyrite, chalcocite and cuprite and the ores extracted are chalcopyrite and chalcocite from chalcopyrite and chalcocite respectively. Next metal is zinc and the minerals are zinc blende, zincite and calamine and the ore extracted is zinc blende from the mineral zinc blende. So this was all about the D block elements. Now we move on to study the F block elements, which are also called as the inner transition elements. The inner transition elements consist of lanthanoids and actinoids. The elements whose f orbitals get filled up by electrons are called as F block elements. The F block elements are placed separately at the bottom of the periodic table and they consist of 6th and 7th period. Since the f orbital lies inside the d orbitals when compared to the transition metals, hence they are called as the inner transition elements. F orbital has a capacity of occupying 14 electrons. The lanthanoids are characterized by the filling up of 4f orbitals and the actinoids are characterized by filling up of 5f orbitals. Let us now study some properties of the F block elements. The properties of the F block elements are similar to the D block elements. In F block elements, the electrons are added to the F subshell of n-2 level. They are placed between n-1d and ns block elements. Lanthanoids begin with the atomic number 57 and end with 71. Lanthanoids are also called as rare earth elements because they are present in very less amount in the Earth's crust. Also, there was difficulty in extracting them economically. In pure form, the metals of lanthanoids are soft and they have moderate density in the range of about 7 gram per centimeter cube. They also have high melting and boiling points. Lanthanoids have properties similar to group 1 and 2, which means in metallic state they are very reactive. Also, they resemble the alkali and alkaline earth metals in the reactivities. For example, they react with water to give the formation of metal hydroxides and hydrogen gas. The common oxidation state of lanthanoid is observed to be +3. Apart from that, +2 is also an important oxidation state. All the lanthanoids elements are stable and form ions of M2O3 type, where M is the metal ion. Higher oxidation states are unusual for lanthanoids except for cerium, which exhibits the oxidation state of +4. The energy which is required to break the lattice is the energy of atomization, and it is comparatively less when compared to that of transition metals. And the reason behind that is, we know that transition metals, they are hard while lanthanoids are soft. So more amount of atomization energy is required to break the hard lattice of transition metals. If we observe the ionic radii, then it decreases from 117 picometer of lanthanum to 100 picometer for lutetium. The reason behind this is, the 5 orbital do not shield the outer 5s and 5p orbitals, and hence the effective nuclear charge increases, and because of that the electrons which are present in the 5s and 5p can be easily removed, and the atomic size or the ionic size gets reduced. All the lanthanoids form hydroxides of the general formula LnOH thrice. Here Ln equals to any element of the lanthanoid series. The hydroxides formed are ionic and basic in nature. We are aware that the ionic size decreases from lanthanum to lutetium, hence lanthanum hydroxide is the strongest base while lutetium hydroxide is the weakest base. Lanthanoids also react with nitrogen and halogen to form nitrides and halides of the formula LNN and LNX3 respectively. The common oxidation +3 of lanthanoids is obtained by losing 3 electrons from the outermost shell. When lanthanoids are heated at a temperature with carbon, it forms carbides with the formula LNC2. In the +3 oxidation state, most of the lanthanoids are colored like green, yellow and pink, and this is because of the transition of f orbital. We studied DD transition, because of which the color emerges. Similar is the case here. In case of transition metals, the color of the compound would depend upon the nature of the ligand. However, in lanthanoids, it doesn't depend upon the ligand. Let us now study some properties of lanthanoids. Lanthanoids are soft metal and they have a silvery white color. They have moderate densities in the range of 7 gram per centimeter cube. The color and brightness of lanthanoid elements decreases when exposed to air. They are good conductors of heat and electricity. Except for promethium, all are non-radioactive in nature. The atomic and the ionic radii decreases from lanthanum to lutetium, and this is called as lanthanoid contraction. Binding of water is very common in lanthanoids. Coordination number of the complexes formed are usually above 6, that is 8, 9, even up to 12. Coordination number is the number of atoms ions which are bonded to the central metal ion. The lanthanoid elements are highly paramagnetic. However, gadolinium becomes ferromagnetic below 16 degrees Celsius. There are other heavier lanthanoids like ytterbium, terbium, thulium, holmium, etc. They also become ferromagnetic, but at a considerably lower temperature. Magnetic and optical properties, they are highly independent of environment. Optical properties means properties related to light. Let us now study the electronic configuration of lanthanoids. The general electronic configuration of lanthanoid is gas core of xenon 4f0 to 14, which means the electrons in the f orbital ranges from 0 to 14. 5d 0 to 2 and 6s is completely filled with 2 electrons. As we know, the lanthanoid starts with lanthanum and ends with lutetium from the atomic number 57 to 71. So here is the expected electronic configuration and the observed electronic configuration. Lanthanoid involves the filling of f orbitals. The energy of the 4f and 5d orbitals is very much close by. In case of lanthanum, the 4f orbital has higher energy when compared to the 5d orbital, and that is the reason lanthanum shows the electronic configuration of 6s2 5d1 and not 6s2 4f1. Let us take the example of gadolinium. Its electronic configuration is 4f8 6s2. So if one electron from F is transferred to the 5d orbital, then the 4f orbital becomes stable by having half-filled 7 electrons. Even in case of lutetium, there is 1 electron in the 5d and there are 14 electrons in the 4f orbital, hence making it stable with completely filled orbital. Ionization energy is the amount of energy required to remove the valence electron from an isolated gaseous atom or molecule. Larger the nuclear charge and smaller the radii of electron, larger is the ionization energy. However, the ionization energy is more for half-filled and fully filled orbitals. The ionization energy of the lanthanoid elements is larger than S block and smaller than P block elements. Next is the oxidation state of lanthanoids. +3 is a common oxidation state for all the elements belonging to the lanthanoid series. In this, 2 electrons from S and 1 electron from D is removed. The electrons in the 4f orbital, they are strongly screened by the electrons which are present in the inner 5s and 5p orbitals, and that is why they do not participate in the bonding. However, there are elements which show the oxidation state of +2 and +4. This oxidation state is possible only if there are 0, 7 or 14 electrons in the f orbital. For example, cerium 4+ ions, europium 2+ ions, terbium 4+ ions and ytterbium 2+ ions. The next trend is color and spectra. Lanthanoid ions can have electrons in the f orbital. When a frequency of light is absorbed, the light transmitted exhibit a color complementary to the frequency absorbed. So the inner transition element ions can absorb the frequency in the visible region because of FF electron transition and hence produces the color. Many of the lanthanoid elements are silvery white. Lanthanoid elements ion which are having a +3 oxidation state are colored in solid state as well as in aqueous solution. The color of the cation depends upon the number of unpaired electrons present in the f orbital. Next is atomic and ionic radii. As we move along the lanthanoid series, there is a decrease in the atomic and ionic radii, and this steady decrease in the atomic and ionic radii is called as lanthanoid contraction. As we move from one element to another, the nuclear charge increases by 1 unit because there is addition of electron in the 4f subshell. So the electrons which are present in the 4f subshell, they shield each other poorly from the nuclear charge due to their diffused nature. So with the increase in atomic number and nuclear charge, the effective nuclear charge experienced by the 4f orbital increases, and as a result the 4f orbital contracts for each successive element. Let us now study the applications of lanthanoids. Lanthanoid elements are present in all our houses. It is present inside the color of television tubes. When electrons are bombarded on lanthanoid compounds, they emit visible light on a very small wavelength. So, a mixed oxide of europium and ytterbium releases an intense red color when bombarded with high energy electrons. The optoelectronic applications use lanthanoids ions as active ions in luminescent materials. The most notable application is the use of ND YAG laser. It stands for neodymium doped yttrium aluminium garnet. Lanthanoids are also used in superconductors, hybrid cars, and permanent magnets. So this was all about lanthanoids. Now we move on to study about actinoids. The last row of elements in the periodic table forms the actinoid series. Actinoid series begin with the element thorium, with the atomic number 90 and ends with lawrencium with the atomic number 103. Most of the elements are not found in nature. They are radioactive and man-made. The elements of actinoids have high densities and high melting and boiling points. Actinoids are less reactive than lanthanoids. The elements of actinoid series show variable oxidation state. The common oxidation state of actinoids show loss of outer electrons. In the initial elements of actinoids, there is ready loss of electrons from the 5f subshell, which indicates that these electrons are much closer in energy of 7s and 6d electrons. So, the 5f, 6d and 7s have similar energies. For thorium, protactinium and neptunium, difference in energy level is small, and that is why the electrons occupy either 6d or 5f orbital. In actinoids, the 5f orbitals have considerably lower energy, and thus from plutonium onwards, the 5f orbitals gets filled up in a regular way. The general electronic configuration of actinoid is the noble gas core of radon 5f0 to 14, which means electrons are filled up in the f subshell in the range of 0 and 14. 6d 0 to 2 and the 7s is completely filled with 2 electrons. The most common oxidation state of actinoids is +3, which is formed with the loss of 2 electrons from S and 1 electron from D. There is a ready loss of electrons from the 5f subshell in the initial elements of actinoids, which indicates that these electrons are much closer in energy to 7s and 6d electrons when compared to the 4f electrons, which are close to 6s and 5d electrons. Hence, we can say that 6d, 5f and 7s have similar energies. As the ionic radius decreases, as we move across the actinoid series, it is called as actinoid contraction, and it is due to the poor shielding which is offered by the f electrons. Let us now study some properties of actinoids. Actinoids also appear silvery white in color. They are highly reactive radioactive elements. They experience decrease in the atomic and ionic radius as we move across the series, which results in actinoid contraction. The most common oxidation state of actinoid series is +3, but the initial elements of actinoid series also exhibit higher oxidation states. What are the applications of actinoid? They are used as a major source for indoor lighting. The incandescent lamp which were discovered was because the oxides convert the heat energy into intense light. Actinoids are also used in defense operations, in the production of energy and nuclear weapons. Plutonium is used in nuclear reactors and also in nuclear bomb as well. Many actinoid elements are used in power plants and also for the generation of electronic power. Here is a table which gives the difference between lanthanoids and actinoids. So first we shall see the similarities between lanthanoids and actinoids. That is, both the series show a +3 oxidation state. Then in both the series the f orbitals are filled gradually. The ionic radius of the elements in both the series decrease with an increase in the atomic number. That is because the electrons get added up in the shells. The electronegativity of all the elements in both the series is low and they are said to be highly reactive. The nitrates, perchlorates and sulfates of all the elements are soluble, while the hydroxides, fluorides and carbonates are insoluble. The differences that you see among the lanthanoids and actinoids are: lanthanoids show a maximum oxidation state of +4, while actinoids show oxidation state +3, +4, +5, +6 and +7. Lanthanoids do not form complexes easily, while actinoids they have a greater tendency to form complexes with ligands such as thioethers. Now all the lanthanoids are non-radioactive except promethium, but actinoids are radioactive in nature. Lanthanoids do not form oxocations, but actinoids do form oxocations. Most of the lanthanoids are colorless in nature, but if you look at actinoids, they form colored ions. The last topic of this chapter is postactinoid elements. The elements having atomic number greater than 92 are called as transuranium elements. Elements with atomic number 93 to 103 are included in the actinoid series, while the elements with the atomic number 104 to 118 are called as the postactinoid elements. The postactinoid elements which are known so far are the transition metals. These elements are called as postactinoids because they have properties similar to actinoids. As of now, there are 9 postactinoid elements which are synthesized in nuclear reactions. It is very difficult to study their chemistry because of the short half-lives which they possess. There are some similarities which are observed between the postactinoid elements with transition elements and actinoid series, which are rutherfordium forms a chloride RfCl4, which is similar to zirconium and hafnium in the +4 oxidation state. Dubnium resembles both transition metal niobium and actinoid element protactinium. So this was all about the actinoid series. With this, we finish off this chapter.